When I introduce you, I'll just
Come over here. Okay,
I'll just push out of the
sounds good. Good.
When
Oh, okay. This is gonna give
when I
me
introduce
snap.
you,
All
I'll
right,
just
come over here. Okay.
just-
Okay, now I closed out of that, so they can hear that online.
And staying in this meeting can send you the email to, absolutely.
Oh, you had to give consent?
did.
It's probably this fan on my computer. Is that what you're hearing?
Yeah, I'm wondering. Steve and or Brian, are you guys hearing a lot of fan noise?
No, I can't hear anything over my fan.
Okay, good, because we can hear the fan here. Her computer's
About to take off.
time.
Yeah.
So much knowledge packed into it. It's about ready to explode.
Yeah, Max. Yeah.
What?
I could've done that.
Oh, yeah.
You could've brought it in. I know, it's in my.
Wow, go get it, yeah.
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 Just not an old Mac, you know?
Yeah, perfect. We all have iPhones too, yeah. This is an Apple defense,
It really is.
sponsored by Apple.
That would be actually great. I chatted.
Nice.
Well, it's definitely the best graphics.
Thank
No doubt about that. Beautiful.
Thank you.
That's true, yeah. I have issues to fill.
Well,
Not ashamed, I will not be
clearly you
ashamed.
can see it online now, was probably on the ship at that time.
Oh, no way.
Yeah, he was out there for the first days.
Wow.
Were you there for the first couple of days, Steve?
What was that?
Were you there for the first two phases of ice?
I was there for the first leg, which was the first 6 weeks, and then for 9 of the last 12 weeks.
Yeah, okay. So Steve, I was a co-advisor for his masters. And, yeah.
And now he's on my committee.
Wow.
And so we got connected with this.
That's really cool. Yeah, she's been telling me all about it. And it sounds like such a cool project, but also quite scary. About all the ice melting and all your equipment is out there and you have to go out and take everything down and
I saw Steve take a swim,
really.
yeah, in late, in June.
How long have you been in this
Remember,
water?
remember, the equipment that was left out there on the sea ice overnight, Steve?
Yeah.
How long can you be in the sea ice, like taking a swim?
Oh, we have survival suits on.
Okay.
It was pretty. He was
It
crossing.
looked scarier than it was.
It
It
looks,
was one of those things where I knew it was going to happen sooner or later, so I was ready for it. I think the people watching were kind of surprised.
I would be.
We were watching from the bridge of the ship.
A cold form.
And then the day that we removed everything from the sea ice, which was probably later that day, because it was no. I went up to my waist. We were walking around and taking down the meteorological tower and just in a hole. Like, oh, I don't think I'll want to get here.
Wow. Do the survival suits have like life vests
They-
type things?
Yeah,
A little bit? Gotcha.
yeah. The thing is it's so by that time, everything's melting. So the surface is like water and ice, so it's zero.
Yeah.
You know, so it's warm. It's hot out. You got this. So, you don't really want to wear it.
I bet.
Absolutely, but
Yeah.
it's super warm.
I bet. Oh, man.
Good. So you just got almost, nothing on underneath, like this.
Yeah.
Long underwear and that was it, and t-shirt, because
Wow.
you're just like.
Yeah. And so are these all the images caught later on?
This was helicopter,
Hello, wow.
or not it was maybe, I think this was from Ice Bridge, so it's probably plane. Yeah, yeah, I am planes, yeah.
Flew out, that's how I got out there, I flew out in a Puma, a Super Puma helicopter from From
That's so cool.
long year, yeah, it's like a 2 hour helicopter ride.
Really? They could do, do they have to refuel?
Yes, they. do.
Yeah, okay, I'm just gonna, wow, that's a long time to be up in the air.
No, we
That's amazing.
flew over the island of Svalbard
Uh-huh.
and we refueled and then we went out to the ship.
Right,
Which was north of Svalbard.
well, I've seen the tracks,
You'll
I
see the
have,
track.
yeah,
And
with all the stuff.
and I suspect they refueled them.
Wow, wow. So is it also like kind of a life flight situation just in case? Or are you guys on your own? Hazard pay.
We did try to stay within range of the helicopter for safety purposes.
Very
But
smart.
not direct flight range. They would have to refuel at the northern tip.
Makes sense. Wow. Well, I admire the work that you guys do, that's for sure.
I got a couple of pictures of the ship. With my camera inside, I had a few kind of circling, landing on the back of it. Yeah, it was cool.
That's awesome.
Yeah, the view was cool. Hi, Long.
Morning, Sarah.
Good morning. Thanks for pointing out that I had the invite PM instead of AM yesterday. That was a big
Yeah,
mistake.
I just couldn't figure out why it does not appear on my calendar. Was actually pretty late in the day.
Yeah, that was a good call with spotting that for sure.
Were you trying to get an extra 12 hours for practice?
Yeah. I was trying to really mess up Steve's sleep schedule. That was my goal.
Yeah, it did confuse me why it came up at 5:30 in the morning tomorrow. But I wasn't blaming you, I was blaming Microsoft, so.
Okay, we could keep blaming Microsoft. I'm okay with that.
It usually works.
Hi, Brian.
Morning.
Good morning. Looks like we're just waiting for Hiping now.
Yeah, I think I just saw Amin arrive. I think he's coming.
Okay,
I
nice.
don't know whether Ana Carla is coming online or offline or.
Did you send her the link? Cause I didn't send the link to her because I didn't know.
I can't remember if I did or not,
Okay,
but I did. She knows I have it.
okay.
And the same for them. I did send them text.
How dare him not be early.
I.
Yeah, well, if you ever try to live stream to YouTube, make sure you try to set it up like a week in advance. Because you have to like do some stuff and then wait 24 hours and then do some more stuff and wait 24 hours. So it's like kind of an annoying process.
I'm so glad that you figured all this out before, well, before my defense.
I'll set it up for you. No, Hiping just logged on.
If you don't mind, I will just go around down the hall and see what's happening there.
Okay, sounds good. Vaughn is just running down the hall to get people who are late and then I'll get started.
Oh, I'm like,
Hi,
are
Ben.
you coming? What do you mean, what? That's where mom's saying. And then there's muffins and.
Muffins and coffee.
The muffins are very good.
Are they good?
Yeah.
Good, I'm happy to hear that.
We're both having the cinnamon, but they're pretty good.
Yeah, no one's tried the blueberry yet.
Hello. Come on down. Somebody has to be side of the table. So I must start on the road. I hope you're still thinking about 3 days to be there. Here's Bill.
Oh, online.
Yep.
Nice. I don't know.
Great.
Thank you. Just greeting everybody. You're the
Yeah.
greeter.
I will send the link to Anna Carla, because I know she wanted to.
Okay. Oh,
Talking, chemistry. First year chemistry. She's here.
no, unfortunately not. Well, maybe fortunately, I don't know, but
He's a great person.
Oh,
So,
then unfortunately.
enjoy your defense
well, maybe we should have invited him.
next time.
My fault. No, next time. Yeah, plus.
All right, well, let's get started.
Okay.
I'm gonna come over here. Hi, everybody. We've got a few people in the audience here, and it looks like we've got the entire committee. Today is the PhD defense for Sarah Murphy. Sarah came to us from Lyndon State College. She got her bachelor's there in atmospheric science, and she arrived here in 2015. And she's been working on this project with NICE that she'll describe. During this time, she also made a couple of field trips to Summit, Greenland, to help with the ice caps project, and got a little polar field work in. In addition, she got a fellowship at PNNL to work there, but unfortunately the pandemic, you were going to work there for 6 months, something like that. Yeah, and the pandemic that put a squash on that, so she ended up doing it remotely. But we were very fortunate that Hai Long Wong, who's was her PNL advisor, stayed on and continued to help advise her. So that's kind of her history since she's been here. I wanted to introduce the committee since we're all online. The committee members from WSU are Huping Liu, who's an active faculty member here at LAR, as well as Brian Lam, who is an emeritus professor from LAR. Hai Long Wong from PNNL is also a committee member who helped a lot with the modeling. And then Steve Hudson is at the Norwegian Polar Institute, and he was instrumental in getting me and then Sarah involved in the NICE field campaign. So I think, was there anything else I was supposed to I thought there was the third thing on my list. I can't remember.
I don't think so.
But so yes, this is what it is, just to let everybody know how the exam will go. Sarah will talk for about 50 minutes or so, and there will be time for general questions. If you have any questions here, either online or in the room here. If you're online and you have a question, I guess it's just a committee. I think we might be expecting a couple more people on. Oh, no, there's quite a few more people.
Right there.
Oh, yeah. Okay.
Yeah, looks like we have
So we've got a lot of people online. If you have any questions, just post to the chat, and we have a chat monitor. We have an actual monitor here. So just post something in the chat, and Sarah will repeat the question and answer it here. The questions usually go 5 or 10 minutes from the general audience. Then we'll excuse everyone, including Sarah, and the committee will confer for a few minutes and get our act together. And then we will bring Sarah back in for the exam. So that's the way it's going to go. So without further ado, I'll turn it over to Sarah, and she can go through her presentation. Thanks, Sarah.
All right. Hi, everyone. Thank you for being here. I'm just going to get my screen ready and hide all of this Zoom stuff. to hide this and hide this. All right. So today I'm going to be talking about measuring and modeling of the Arctic atmosphere during the Norwegian Young Sea Ice Field Campaign. And so this is an outline of my talk. I'm going to spend most of the time on the modeling and the results section. These correspond to chapters in my dissertation. So this is where really the meat of the project is. And then I'm going to sum that up with some recommendations and conclusions. So first, I want to talk a little bit about the Arctic and motivate this research. So here in this figure, over here, we can see this is the warming trend up here. It's from 1990 to 1980, and then down here is from 1981 to 2020. So this is just 20 years, and up here is 80. And so we can see that in these 20 years, we have a lot stronger warming in the polar regions. These dark red colors indicate a stronger warming trend. And so we can see that the polar regions are warming much more quickly than the mid-latitudes and elsewhere on Earth. To go along with this, the sea ice is also declining. So this figure is September Arctic sea ice area. And so September is going to be the lowest sea ice area because that's the end of the summer. This is our trend from 1950 to around 2015 of our sea ice area. And then these are projected trends with a bunch of different emission scenarios. And so we can see that in 3 of them will be practically ice-free in the summer by 2100. And then in these 2, we'll still have significantly lower sea ice area. So with this is sort of trending toward an Arctic that has less multi-year sea ice or sea ice that may melt a little bit in the summertime, but still we have an ice cover on the Arctic, on the ocean then, in favor of first-year sea ice, which is sea ice that will melt out entirely in the summer and then refreeze in the winter. So I'll be using the terms first-year and multi-year sea ice throughout this presentation, and that's how I define them. So since first-year sea ice is becoming more prominent in the polar regions, it's becoming more important that we know how to model this. So first-year sea ice can complicate atmospheric models due to a couple of things that I call the special features of the atmospheric models or of the system and over first-year sea ice. And so this figure here shows everything that's going on. And we can see that we have quite a complicated system here. We have our open water with currents and our ocean circulation, but we also have a variety of different snow surfaces, albedos, and also melted water and different water contents of the snow and ice. So with all of this comes a lot of other interactions with the surface in the atmosphere that we don't necessarily see in either the mid-latitudes or over multi-year sea ice, where we don't have such an inhomogeneous surface. So this leads me to my research questions. First, what cloud properties were observed during the Norwegian Young Sea Ice Field Campaign? And I'm going to describe this field campaign in the next section, but this is the field campaign that took the measurements that I'll be talking about throughout this entire presentation. I also wanted to know how turbulent fluxes and clouds interacted with this young sea ice, how the polar wharf model performed when compared to the observations. So the polar wharf model is the model that I'm going to be using throughout this presentation, and that's just the model that I'm using to represent the Arctic atmosphere. I'll talk about that more in a little bit. I also wanted to know if there were certain cloud microphysics and boundary layer schemes that were better suited for these conditions. And I'll talk a little bit more about that, what that means when I get into like the meat of the modeling. And then I wanted to know if I could improve the model over first-year sea ice. So first I want to talk about the N-ICE field campaign. So the background here is a map. As we can see, here we have Greenland, and then down here is Washington with the star. This island here is Svalbard, and so this ship was frozen into first-year sea ice just north of Svalbard, where we have this cloud, and it was allowed to move with the sea ice. So this figure down here shows the ship tracks, or where the ship was as it moved with the sea ice. You can see that there's some breakup in these lines. So like we have 1 and 2 and they're discontinuous. And that's because as the ice broke up, the instruments on the ice needed to be packed up and motored further into the sea ice. So we are going to be seeing some gaps in our observations throughout this talk. I refer to these as flows or ice flows throughout this presentation, and I have the dates listed here. But generally 1 and 2 I refer to as winter because these were in January through March, and then April through June is our spring and summer period. So now I want to talk a little bit about how the observations were taken at NICE, so you can have a little background of where the data that we're working with comes from. So first we have this meteorological tower. It was mounted over the sea ice, and we have 3 different levels here, and it measured temperature, humidity, and wind speed and direction at all of these levels. We also had an eddy covariance system, and so this measured turbulent fluxes and or it measured wind, water vapor, and temperature, and then turbulent fluxes could be calculated using LICOR's Eddy Pro software. And so when I'm talking about measurements, sometimes they're labeled as Eddy Pro, and that refers to the software that actually processes the data. We also have these radiometers. They were mounted about 1 meter above the surface, and we have upward facing and downward facing, and they take measurements of the long wave and short wave radiation coming from both directions. We had radiosondes or weather balloons that were launched twice daily, and these measured temperature, relative humidity, wind speed and direction, and pressure up through the atmosphere to give us an idea of the atmospheric structure. Lastly, we had a micropulse LiDAR on the ship. And so this diagram shows what how the LiDAR works. So here it is mounted on the ship, and it sends a laser beam up to the cloud and reflects a portion of it back to the LiDAR sensor. And the way that it's reflected back and the amount reflected back can tell us information about the clouds. However, this does only tell us information about the clouds directly above it or directly above the ship. So whenever I'm talking about cloud fraction with this LiDAR, it is the fraction of clouds observed directly over the ship. So now I'm going to take a drink really quick. And I'm going to get into the modeling section. So first, I'm going to describe the Weather Research and Forecasting Model, or WRF, and what makes it a polar WRF. And then I'll talk more about actually digging into the model. So for WRF, I ran the model in this domain here. So our parent domain, or the more coarse outer domain, has 9 kilometer by 9 kilometer grid cells, and the inner domain here has 3 kilometer by 3 kilometer grid cells. So this means that whenever we have a measurement or a model observation, model value, it's the value of the 3 kilometer by 3 kilometer grid that the ship is in at that point. So the WRF model itself is a numerical weather model, and it's used for both research and operational applications. So it's pretty flexible for the user to do what they wish with it. And the polar WRF has polar improvements for modeling in the polar regions. I ran the WRF model 2 times, once for winter in January through April, and then again for spring and summer in April through July. And I used ERA interim for my boundary and initial conditions, and I did give it sea ice thickness, ice extent, albedo, and snow depth from biomass and SSMI to give it all the information that it needed to get hopefully everything correct. This diagram here is a simplified diagram of the components of the WRF model, and really I've only picked out the components here that I'm going to talk about in this talk. We have our clouds, and so this combines the cloud microphysics and cumulus schemes, but these are 2 separate things. And then our surface has our land surface model and our surface layer scheme. So I'm going to refer to each of these as schemes because they have different chunks of code that essentially can be selected, and they're tuned for different things by different groups. So these are available for the user to select in WRF. With WRF, we can run the model as a real or an ideal case. And I point this out because I run it in both different ways throughout this talk. So for the majority of it, we run it in the real way. And so that runs it as the full model. And this is usually what we think of when we discuss atmospheric modeling. And this is used both in research and operational purposes. But I also run the model in an ideal way, which gives us an idealized atmosphere and sort of gets rid of a lot of the local influences, so that sensitivity studies and testing can be done with model without spending the computational expense of running the real model, which can take a lot of time. So what makes the WRF model polar WRF that I'm working with are some advancements that are in the cloud microphysics, the boundary layer, and the land surface model. And so these have been tuned for better like heat exchange through the surface and better parameterizing of the atmospheric structure in the polar regions. But this was tuned for multi-year sea ice because this was tuned using Shiba observations. So it's not necessarily tuned for what we're seeing at an ice, but this is why we need to test it. So for my model simulations, I used RRTMG for my radiation scheme and the NOAA LSM for my land surface model. And these were held constant throughout all of my different WRF runs. The NOAA LSM is the land surface model that has the polar improvements added to it. So this is the model that will be performing the best in the polar regions, hopefully. The boundary layer scheme and the cloud microphysics scheme, I varied because I wanted to see if either of these schemes did, or if either scheme for either of these did better or worse. So this is a table of all of my different model simulations. So this is how I'm going to refer to each of these model runs throughout this talk. These are our cloud microphysics schemes and have different ways of parameterizing the cloud droplets and the phase of the cloud and things like that. Our boundary layer scheme is shown here, and these have different ways of estimating some different constants and other parameters. And so as I refer to these throughout this talk, each abbreviation starts with the letter of the cloud microphysics scheme and then has the boundary layer scheme and as the second half. So when I say the GYSU scheme, I mean the model run that uses the Goddard microphysics scheme and the Yonsei University boundary layer scheme.
And one clarification, weren't these selected based upon a literature review that you did of past polar?
Yes. Yeah. So these were selected based on a literature review, and these were used globally and in the polar regions. The Morrison 2 moment scheme actually is the one that is tuned for the polar regions, but we'll see that that doesn't make it the strongest scheme in the polar regions. So this is the same diagram of the components of the WRF model, and I'm going to be returning to this throughout this presentation to sort of show us where we are within the grand scheme of the model. First, I want to talk about the surface layer and some of the processes that are occurring then or there, and then I'm going to talk about processes in the clouds, and then we'll get to my results. So the surface in the polar regions or over first year sea ice looks something like this. I want to direct a net radiation. So this is the short wave, the difference in the downwelling and upwelling short wave and the difference in the downwelling upwelling long wave. And so we can see this in these two terms here. And then we have our HS, or sensible and latent heat fluxes. And so these are our turbulent fluxes, and we can see these here. And then we have these two terms here, which are referred to as our residual sometimes. FS is our storage within the within the ice surface, and C is our ocean heat flux. So this is everything that is occurring. We're going to focus on this side of the equation and not necessarily this side because I'm focusing on the atmosphere purely. also want to note that in our area where we're talking about, since it is the polar regions, we're going to have a lot more reflection from the snow and ice surface than we would if we were in the mid latitudes. So I've been using the phrases sensible and latent heat flux a little bit, and I just want to define those for us really quick. These are the turbulent fluxes. I will also refer to them as that. The sensible heat flux is the conductive heat transfer. And this is defined as positive when the atmosphere is warmer than the surface and the heat transfer flows from the atmosphere to the surface. And then our latent heat flux is our heat transfer related to phase change. And so our positive values are going to indicate like freezing, condensation, and deposition. So now I want to talk about some of the things going on with the clouds. So the way that we talk about how clouds influence the radiation at the surface is by looking at the cloud radiative forcing. And so this is defined as our measured radiation minus our clear sky radiation, or whatever the radiation would be in the absence of clouds. So in this diagram here, we can see some of the things that clouds can do to the radiation. So these high clouds, they reflect sunlight, but they also absorb and re-emit the long wave radiation from the Earth's surface. And often have a larger influence in that, the long wave radiation. And then we have our lower clouds, which reflect more incoming sunlight, and they also absorb and re-emit this long wave radiation. So overall, positive cloud radiative forcing is going to mean that we have a warming at the surface, or that there's a net surplus of radiation at the surface, and negative means we have more cooling at the surface due to those clouds. And I just want to note that since we are in the polar regions, we're going to have fairly low sun elevation angles, and that's going to increase our reflectance. So now that we understand a little bit about what's going on in the polar regions, let's look at how the model did. So first I want to look at the winter. And so we have our time series over here, and then here we have model biases. And so that's our modeled minus our measured values. And so this is showing how off the model is compared to the observations. So first I want to point out these ones that have the lowest model bias in these certain categories. So the 2MYNN simulation had the lowest biases in both latent and sensible heat flux. And this was pretty impressive, particularly since in the sensible heat flux, we have some fairly large biases. However, we see that where we have these low biases, we also have fairly high ones. So this shows me that we have some compensating errors going on here. When the model is doing well in, say, the net long wave, it's sort of dumping those errors into the sensible heat flux here and the temperature. Because of this, for the winter, to choose a scheme that performs best, I've chosen the 2MYNN scheme because we have our lowest biases here. And even though this is our highest in the net long wave, we do fairly well here. So we're going to say that this is our best winter scheme. Now, this shows the same thing for the spring and the summer. And so these are our schemes with our simulations with the lowest biases. Our GMYJ has fairly low biases, and then so does our P3 MYJ. So this shows me that the MYJ boundary layer scheme is doing pretty well in the polar regions. So these two schemes, the P3 MYJ and the GMYJ, have a very similar bias for latent and sensible heat flux and the net shortwave. However, we can see that they have pretty high bias, pretty high negative bias in the long wave radiation. And we can see the opposite down here with the 2MYNN. While we have the lowest bias in the long wave radiation, we have some of the highest in the other categories. So again, we're seeing these compensating errors where we have good performance in one variable, we have poor performance in another variable. Because of this, I have selected the GMYJ as our best scheme here. It could be argued that the P3 MYJ looks like the best scheme when looking just at the bias, but the net long wave of the P3 scheme just has some biases that are canceling each other out. That's making it look a little better sometimes. And because this bias is lower, then this one just by a little bit, we're going to select the GMYJ scheme as our best scheme for the spring and summer. So here we can see the whole time series, and just to summarize, the 2MYNN simulation was the best in the turbulent fluxes, worse in long wave radiation, but still was the best for winter. And then in spring and summer, the GMYJ performs best. And one thing that I want to point out when we look at this time series is down here where we have our cloud fraction. This thick black line or gray line that you can see here is our measurements. And the colorful lines are the model runs. And we can see that the model runs are really kind of all over the place with the clouds. So this brings us to some outstanding questions. So what is causing the bias in the fluxes? Why can't we get that right regardless of our cloud and boundary layer scheme? And that the cloud fraction is clearly incorrect in the model. So are the cloud properties also incorrect? What's going on here? And is the inability to, or is the error being introduced due to the inability to portray the strongly stable conditions in the at the surface in the polar regions? So this brings me to my chapter 4 of my dissertation, and this is when I focused on the clouds and the radiation because they kind of go together. And so for this chapter, I really wanted to figure out what the cloud conditions were and how they compared to the model of clouds. So first, I really want to briefly look at the long wave and short wave flux. So this is just flux. This is not the cloud radiated forcing. And so in the short wave, we can see that we have no short wave radiation here, but we do start to have some as the sun rises in March. We have small positive net short wave radiation because of our albedo. Down here, we have our long wave flux, and we see increases in these periods where we have this orange bar. These are our storm periods. So this is when there was likely significant advection bringing air of other properties into the area. And so we can see the same thing going on over here. Our net long wave is generally slightly negative. And then when we look at our net radiation, we can see that because our long wave is slightly negative and our short wave is getting larger with the increased radiation, we have positive net flux in the summer and negative in the winter. So now let's look at the cloud properties themselves. This figure up here shows monthly averages. So here our January average is around 7.5 kilometers, but then the rest of our month average cloud base height is under 3 kilometers. So we had pretty low cloud base heights throughout most of the experiment. And we can see that in this figure down here too, where we have our cloud base height plotted as a time series. And we can see that in January here, we do have those high cloud base heights, but then we have this pretty low cloud deck the entire time. This figure up here is our daily vertical cloud fraction. So this is the percentage of the time during the day that there was cloud detected above that LiDAR. And these are colored by ice content. So a cloud that, or a point that is entirely yellow is a completely ice cloud, and then entirely purple would be completely water cloud. And so we can see that in the winter, we have a lot of ice clouds, but we also have a lot of mixed phase clouds, seeing in these like blues and greens. We also have a period where we did have some water clouds. So we are having a mix of cloud properties happening in the winter. But then when we get into the spring and summer, we can see that there's a lot higher water content in our clouds, or water instead of ice. And so we have a lot of those purple points. We do still have mixed phase cloud here, but we don't have any just ice cloud as far as we can tell here. And then down here, we have our cloud-based temperature, which follows our surface temperature pretty closely after this chunk of higher cloud-based heights, because we have such a low cloud deck throughout the entire experiment. So now let's see how the model did when we look at clouds. So I've pointed out the simulations that we selected earlier with these arrows. And up here we have winter, down here is spring and summer, and it's colored by clear versus cloudy. So the yellow is going to be entirely cloudy, and then the purple is going to be entirely clear. So we can see that in the observations in the winter, we have a lot of cloudy, but we do have some clear periods. But the models just really aren't picking up, excuse me, the models are not picking up the clear and cloudy pattern quite right in the winter. We see the same thing going on in the spring, but the models are showing significantly decreased clouds, particularly compared to the observations. We have very low cloud cover in all of the simulations. We do have this one completely clear sky day here. That was the only completely clear sky 24-hour period during the spring and summer in the observations. And that is captured fairly well by the models, but this isn't necessarily surprising since they underestimated cloud fraction the entire time. I would hope that it could at least get some clear sky correct. But overall, it did pretty poorly in the cloud fraction. And I observed cloud cover pretty consistently throughout the expedition, but Polar Wharf shows much too low of cloud cover compared to the results. So how can this influence the surface fluxes? First, let's look at what the cloud radiative forcing is in actuality, what's really going on with the cloud radiative forcing. So this figure up here is our winter frequency of cloud radiative forcing values. And this is just the long wave radiation because that's all we have in the winter, primarily. And so we see here we have this big peak around 0. And so that is representative of our clear sky times because 0 cloud radiative forcing, if there are no clouds, they're not going to influence the surface at all. But then we have this tail of a variety of values. And so this represents our cloudy conditions and it represents a range in cloudy conditions. So like we saw before, we did have a range in our phase and in height in the winter, and we can sort of see that here. In the spring and summer, we have both the shortwave and the long wave radiation. And so our long wave is shown in blue here and shortwave is in this pink color. We see a pretty big spike in the long wave radiation between 60 and 80 watts per meter squared. And this is representative of those low, thick clouds causing significant long wave cloud radiative forcing near the surface. And we had pretty consistent cloud properties throughout with that low cloud deck. And so that's why we're seeing a pretty large peak here, whereas we didn't see that in the winter. Our shortwave is primarily negative, and so that's contributing to some cooling at the surface, and the long wave is contributing to warming. But the long wave warming is more significant than the shortwave cooling, and we're getting positive values throughout pretty much the entire experiment. So these figures show a time series of our observed cloud radiative forcing, and then these are the two model simulations that we determined were best. The 2MYNN was best in the winter. The GMYJ was best in the spring and summer. So for our shortwave cloud radiative forcing, we're seeing that in both of the different model runs, the clouds are not influencing the surface anywhere near enough in this spring period. When we get into later in June, the cloud radiative forcing picks up a bit. So it starts to match the observations a bit better, but overall it underestimates quite a bit. In the long wave, the 2MYNN seems to capture the peaks well, but it doesn't really capture these low values very well. The GMYJ does, but doesn't capture the peaks quite as well as the 2MYNN. So this is showing that the 2MYNN is better at simulating more optically thick or clouds that influence the radiation more, versus the GMYJ is producing more clouds that are opaque or less cloud in general. And then we see the same thing in the long wave in the spring and summer, where we have very low cloud radiative forcing values for the GMYJ, but fairly high for the 2MYNN. And this is pretty interesting because if you remember, this GMYJ is the one that performed best in spring and summer. So even though it's performing well, it's still getting these cloud properties incorrect. And then down here we have our net, which is the sum of these two. And so this is the same as our long wave in the winter, but then in the spring and summer, it's the combination of these And the GMYJ just really underestimates the cloud radiative forcing, and then the 2MYNN overestimates it. So overall, even the simulations with the lowest biases aren't accurately capturing the cloud radiative forcing. So something's going on with these clouds. They're incorrect in the model. Is that what's causing the incorrect fluxes? What's going on here? So to answer this question, I am going to step into the planetary boundary layer and look at calculating the surface fluxes. Basically, what I want to do here is figure out if we can even accurately estimate these surface fluxes independent of a model. Because of those strong, the strong stability seen in the polar regions, it could be difficult for us to estimate. So I've estimated this using two different methods to calculate latent and sensible heat flux. One is the bulk flux algorithm, which is what WRF uses, and it's based in Monin and Obakov similarity theory. And then the second one is the maximum entropy production method, which is tested in the polar regions and is a little bit easier to use because it only requires one level of measurements. So if we look here, we can see the different variables that the bulk flux algorithm and the maximum entropy method use. So the MEP, that's what I'll be calling this method, it uses the net radiation, the transfer equations, and then temperature and specific humidity only at the surface. The bulk flux algorithm uses the specific humidity and temperature at two levels, bless you, and the wind speed and these transfer equations. So I want to take a step into these transfer equations for a minute. So these are based on, the transfer equations are based on scaling equations, and the scaling equations depend on the surface stability. So this figure here shows the stability range that each scaling function can be applied over. So all of these names are the different sources or the people who have created these scaling functions. And so the scaling functions are relationships between these variables that depend on the stability. So often these equations have a few, or these publications have a few different equations depending on the stability. So for example, the Swain-Bank equation is only applicable for the very strongly unstable and like moderately unstable conditions. But then we have other ones that are available only, or that are applicable only in stable conditions. So it's important to consider what ranges of stability these equations are applicable over, because we have strongly stable conditions in the polar regions. You'll see these arrows, and what these indicate is that the scheme or the equations claim that you can use at any range of stability. So they don't just stop at 2, you could use that at any stability. So over here, I have some model biases. And so what I've done is I've taken the MEP equation and the bulk equation, and I have used each of these scaling functions to calculate the scaling function to go into the transfer equation, and then I calculated the sensible and latent heat flux. So the equations with the lowest bias were the Beljars and Holslag, the Handorf and the Andreas. This G and P, as I call it, scheme also had fairly low biases, and then we have our lowest sensible heat bias in the Spusinger equation. However, some of these equations also have fairly high biases. So, for example, in this one, we have a pretty low latent heat flux bias, but then our bias in sensible heat flux is quite large. So, this makes me wary to select one that has a large bias like this for our best scaling function. We also want to look at the ranges that they fall between. So these two schemes here, particularly this one, we have low bias, but it's not being applied over a very wide range. We see that it's not being applied over these stable values, which is what the majority of our values in the polar regions are. So that means that while it does have a low bias, it's probably not even being applied to most of the measurements that we have. So overall, that leads us to Andreas being our best scaling equation because it has low bias and it is applicable for any stability. This equation was designed for the polar regions. The rest of these were just selected due to use in literature and being applied in other equations. But the Andreas et al. Was developed for the polar regions, but over multi-year sea ice. So it wasn't tuned for first-year sea ice like an ice. So I took those values and used those scaling equations with the latent and sensible heat flux equations. So this is for the bulk flux algorithm. So this is the algorithm that a form of this is used within WRF. And so up here we have our latent heat flux, and so that's our phase change. And we can see that the bulk flux algorithm that I calculated has a much wider range of latent heat flux values in both seasons. In the spring, we can see these largely negative values, which indicate melting. But in the Eddy Pro or in our measurements, we see that we have latent heat flux values that are hovering right around 0. And so we're a little suspicious of this because we think that there should be more phase change going on, and we can't seem to get any sort of equation to actually mimic these very, very low latent heat flux values. On the other hand, our sensible heat flux performed much better when I calculated it with the bulk flux algorithm. It follows the trends quite nicely, but it does still have a wide range of values, indicating that there's more heat transfer than we actually measured. Now, if we move into the MEP equation, we can see in the sensible heat flux that we have that same thing going on. We have larger flux values, so more phase change in the equation, whereas our measurements are right around 0. But then when we look at the sensible heat flux, I'm really impressed with the MEP equation in the spring with the sensible heat flux, because it captures the range of flux values much better than the bulk flux algorithm did. It does have some issues here in the winter when it's underestimating the sensible heat flux, and we can see that in the histogram over here. But it does pretty well of calculating this. And if we look at this histogram compared to the one with the bulk flux algorithm, we can even see by that it's capturing that range of values much better. So to sum up the flux equation results, we know that the sensible heat flux can be estimated accurately with both different algorithms. The MEP does do slightly better. So that leads me to believe that we can actually estimate these values when we have strong surface stability, and that's not the issue in the model. Our latent heat flux values were overestimated by both equations. So this needs to be looked into a little more, probably with a different field experiment, just to make sure that the measurements aren't just too small in our situation. So now this leads me to chapter 6, which focuses on the surface layer. And so we're going back to the model. We just were talking about pure equations, but now we're digging into the model where these equations are actually stored. Before we move on to the next slide, I want to point out the surface tables square. So the surface tables are lookup tables that supply the land surface model and surface layer scheme with some constants that it needs to simulate the atmosphere. So one of these tables is a land use table. And so this is just a small snippet of land use table. You'll see this variety of sections here. And so users can select the section when they decide, when they're running the model, users select which section they want to use. And then each section has values for both summer and winter and a variety of land use categories. For this, I've only shown the snow and ice ones, or permanent snow, because that's the land surface that we care about. But in the model, it would know your land surface and use the relevant category. So we use the USGS section of the land use table. And so these were our values for our albedo, surface heat capacity, and roughness length. Now, there are more constants that are present in these tables, but these are the ones that I want to dig into a little bit more in this talk. Before I move on to the next slide and get rid of the other sections, I want you to know that we have this very high surface heat capacity throughout all of the different sections. And we have albedos that are 70 and below in all the different sections. So first I want to look a little bit at the albedo. So these are measured albedos at N ice, and you'll notice that we don't have any measurements for flow 1 because that was, we didn't have shortwave radiation then. And all these values are higher than any of the values that we saw in the land use table. While 3 and 4 maybe aren't representative of the entire summer because we'll see more melt as the summer goes on, these values are still significantly larger than the values we're seeing here. So if I were to make any changes to this table with albedo, I would change the summer to be 81% and the winter to be 86%, judging by our measurements. Next, we want to look a little bit at the roughness length. And so this is an estimate of how much the surface roughness is actually influencing the turbulence. The roughness length in WRF is set to 0.1 meter. But Eddy Pro, the software that processed our fluxes, used 0.001 meters as the roughness length. And I saw that these were fairly large differences. So I took 2 different equations to calculate the roughness length, and I got similar values to what the Eddy Pro software used using both equations. So I can estimate our roughness length to be about 0.001 meters. You could argue that we could raise it to 0.005, but because this is the value that Eddy Pro uses, that's the value that I'm also going to stick to. So then we have our surface heat capacity, and these values are quite large. We believe that the model is just setting this to an infinite value. And so bringing this down a bit would probably give us more accurate results. So I've calculated the surface heat capacity of the snow here and then of the ice over here. And so we can see it's still quite a few orders of magnitude smaller than our surface heat capacity we have up here. And so I selected 6 times 10 to the 5 as our surface heat capacity for this, because that is an average of the snow surface heat capacities. So if I made my own section in the land use table, I would make this section, call it N ice, and these are our values that I would use. So that's exactly what I did. I created a section in the land use table and I put these values in for it, and I ran an idealized model. So this is a simplified atmosphere just for a sensitivity study, and compared my results. So I chose 3 small case studies for this. We have a winter cloudy case, and these values are our difference in model bias. So negative values indicate that the model bias has been reduced by making these changes, and positive values indicate that the model bias has been increased by making these changes. So for our winter cloudy situation, we can see that we have improvement in the latent and sensible heat flux and long wave downwelling radiation. But in our long wave upwelling radiation, we increased our bias. But overall, our bias was decreased in many of the sections. So I would say that this section is a win. The spring cloudy, you did a spring cloudy case too, and the spring cloudy case was not a win. So we had decrease in the latent and sensible heat flux. Well, we had an increase in the bias, and then we also had an increase in the bias for the shortwave radiation. We had improvements in our long wave radiation though, but because of all of these decreases in performance, I have sort of deemed this as a bad case for it. And then we have a spring clear case, and our latent and sensible heat flux improved, so did our long wave down, but our short wave and our long wave up did not improve. So I would say to use this with caution. It can improve it in some situations, and particularly in the winter, it seems to perform better, but it depends on which variables are of interest to you. So now let's take a step back and think about what we know so far. So what we've learned are that these model values are incorrect. And we also know that these values are incorrect. So we know the clouds are wrong. This influences the radiation, causes the radiation to be wrong. And we know that the latent and sensible heat flux values are wrong. We also know that when we calculate the latent and sensible heat flux values, just independent of the model at all, we can get those correct values. So we know it's possible, but why isn't the model getting it right? We also know that the constants in the surface table could probably be slightly improved, but these aren't the source of the error in the latent and sensible heat flux. So this leads me to the question of, would fixing the clouds fix these turbulent fluxes? So is this the big red flag in the model, the clouds, and does that triggering other errors? So to do this, what I've done is isolated the surface. I have coded the land surface layer scheme and the land surface model in Python. Is originally in Fortran codes. And I've created just the surface layer into its own independent model. I have given it our measured variables, so our fluxes, our meteorological variables, precipitation, and I calculated the sensible and latent heat flux from this and compared it to those calculations that we did in the previous chapters. And so we can see here our model performance. So our observations are the black dots. Our MEP and bulk are the green and blue stars. So those are the values that I calculated independent of the model. And then the WRF, or that offline calculation of just the surface model, is in pink. So for our latent heat flux, we can see that WRF matches the bulk and MEP better than it matches our observations, which just furthers the belief that our observations are maybe a little suspicious. But in our sensible heat flux, we can see that WRF surface layer model did pretty well. Particularly if you look at the histogram, you can see that the WRF did really well when replicating the range of values compared to the observations. And the MEP also, as we know, did quite well. So those three values within this time series really performed well and together. So this shows us that slight improvements can be made to some of the things within WRF, such as the albedo, the surface roughness, things like that, other surface properties, but that's not the source of our error. And the model could calculate sensible and latent heat fluxes when it was given the correct long wave and short wave radiation. So this just leads us to the conclusion that the clouds are the issue in the model here, and the clouds, once the clouds are sorted out, then other things will sort themselves out. So to conclude, I want to revisit my my research questions and just sort of answer them. So the first one was what cloud properties were observed at NICE, and we saw a consistently low cloud base through most of the months other than January, which had a pretty high cloud base. We saw mixed phase clouds throughout the entire expedition. We even saw water clouds within the winter at one point. And we saw that the cloud influence on the long wave radiation always outweighed the short wave influence. As the sun angle, or as the sun elevation angle, got higher in the sky, the solar radiation did have more of an influence, but it never dominated the long wave. So our next question was, how do turbulent fluxes in clouds interact with young sea ice? We saw that the latent heat flux was very low, which we thought was suspicious. And then we saw that the sensible heat flux was positive pretty much the entire time during the winter and during the summer. During the summer, the values were smaller, but they were still positive primarily. Cloud radiative forcing was positive the entire time. It became less positive as the sun angle, or the sun elevation angle, got higher, but it was still positive. And we saw that the model simulated the clouds very poorly. So next, how does polar WRF perform? Well, as I just said, it performs poorly when it comes to clouds. And we have biases in sensible and latent heat flux and in other variables as well. And we also see a lot of compensating errors. Are certain cloud microphysics and boundary layer schemes better suited for conditions over first year sea ice? None of the schemes were a perfect fit, so I wouldn't say that you should always use this microphysics scheme and this boundary layer scheme. But I do have some suggestions for winter and for spring and summer. For winter, the 2 MYNN was what we saw to have the lowest bias. And then in the summer, the GMYJ had the lowest bias. But again, it does depend on your time of year, and it depends a lot on what variables you're most concerned with. And then lastly, how could polar warp be improved over first year sea ice? This varies season to season, but increasing the surface albedo would be a good start. The user can give the model their own surface albedo, but to increase it in the land use table would be a good starting point for people, or to increase it. And then decrease the roughness length to be more closer to that 0.001 value, and then to decrease the surface heat capacity to be something a little more realistic. And then, of course, improving the clouds would be the major thing that would improve it, which leads me into some of my future questions, potential questions for future work. Could adjusting the cloud microphysics schemes fix the clouds within this? Could we change the thresholds that are being used for partitioning different cloud phases? Would those account for some of the smaller particles found in the atmosphere in the polar regions? Also, would any other methods of estimating sensible and latent heat flux improve our performance? I know that we did well with the equations that we looked at, but it is possible that there are other equations that perform better in the polar regions. And then lastly, what does polar warp show when we compare it to other observations? Are we seeing the same cloud and flux issues when we compare it to Mosaic, a field experiment that was conducted more recently? So here are my acknowledgements, and thank you all for listening, and I would love to answer any questions that you all have. And I'm going to pull up the chat too. Okay.
Any questions in the room? Yeah. Okay, I apologize if you mentioned this and I just missed it, but what is albedo? I'm not familiar with that term.
Okay, so the question was, what is albedo? And so the albedo is the reflectivity of the surface, essentially. The percentage that's shown in the table, whoops, I'm not in the table here. These percentages are essentially the percent of the shortwave radiation that's reflected off of the surface. So these are calculated downwelling, over longwelling, or over upwelling.
Then one other question, how is this this polar warp modeling software that you use maintained? Is it like proprietary or is it open source by another lab or something? Or
So the question was, how is polar warp maintained? So warp is itself is like the core of the model, and warp is maintained by NCAR and UCAR, which is a it's like an organization.
The national lab.
Yeah, it's a national lab.
Research, yeah.
Yeah, so they maintain WRF itself, and WRF is fairly open source. You can contribute to it, and the polar component was developed by researchers at Ohio State University, and so they essentially did something similar to what I've done and dug into the model code and figured out some areas that could be improved for the polar regions. So it's a joint effort.
cool, so it feels like it's being actively developed then.
Yeah, there's active development, definitely.
Do you see the results like contributing to that then?
Definitely, they could be contributing to that. I spoke to somebody at a conference that is working on different like parameterizations of some of the variables within the model, and he was talking about how it would be cool to be able to incorporate that into the model, and so they're very open to like incorporating things like that into it. And I would like to either do that or like do some sort of Python package to help people that are trying to do some modeling of just specific components of the model.
Our original intention was actually to work on the clouds. But when she started to work with PNNL as part of her DOE fellowship, High Long kind of helped us focus more on the turbulent fluxes. And basically High Long has been working to develop this MEP method. He's kind of one of the authors of that. And clearly that appears to be an improvement. I mean, it likely nails the latent heat fluxes, and it certainly improved the sensible heat fluxes. So the real next step is the clouds. That was kind of, it was just too much.
Yeah.
I have a feeling that MEP will be folded in. Because High Long's also using it with the newer mosaic data to compare.
Yeah, just to clarify, the one in the citation isn't me, but that's my colleague collaborator at Georgia Tech. I am interested in putting this into WRF and global model. But I'm glad that Sarah got to the chance to test it offline.
I just want to jump in. Sorry, did I cut someone off? This is Shelley. Great job, Sarah. This is fantastic. I really enjoyed it. It's a little out of my area of expertise, but really nice job. And I just wanted to say thank you for sharing. And I'm going to drop off because I've got another meeting, but great work.
All right. Well, thanks for coming, Shelley.
I wish I could have been there in person. I apologize. I'm getting over a cold, but I'm glad Vaughn got me in last minute into the Zoom. Thank you, Vaughn.
No worries.
Anna Carla has a question here in person.
So as well, great presentation.
Thank you.
Amazing work. Maybe I missed this, but when you were talking about the clouds in the LiDAR, that you said you showed a graph that showed the difference when it was ice, cloud, and water. Like, is that something that is done with the software after the LiDAR measurements? Because the LiDAR just like measure the distance.
Yeah.
How can we determine what is like the ice and the water?
Okay, yeah. So the question is, how do we determine ice versus water cloud with the LiDAR data? Because it doesn't really give you that data. It kind of gives you more raw data. And so we did two different approaches. We used the atmospheric radiation measurement software to calculate those values, but that's not really tuned for the polar regions, and also it misses a lot of stuff near the surface. So we had another researcher, Dr. Robert Stillwell, help us with coding up essentially a Python code that helped identify where we had ice versus water in the clouds.
Do you remember, and quizzing you a little bit here, and this is not necessarily your expertise, but do you remember, it's a fundamental measurement of the LiDAR. It's not just one little light beam that's going up. Do you remember what characteristic of the LiDAR allows us to get that?
It's the phase, the depolarization of the way that the LiDAR beam goes up in two different phases, and then as it's reflected back through droplets, each the phase of the radiation or of the beam, these are like the wrong words for this, but the phase is like changed.
Actually not.
Okay.
You got us.
The phases changed, and the ratio of the phase change between this and this way shows us the shape of the particle, and from that we can trace out the phase. Yeah.
It is a depolarizing LiDAR.
Yeah.
She answered it correct. Yeah, you get a depolarization ratio, and Robert, neither one of us are the experts, but she did a great job answering it. It is that depolarization ratio. So it's not just a backscatter that we get. The backscatter ratio is one thing, but we also get these two numbers that give us this depolarization ratio. Yeah.
We have a question online that I was ignoring, and then I'll get to you. Okay. So Michael asked, he said, you started the talk by referencing the importance of Arctic ice as it relates to the IPCC. Given your modeling efforts, how would you suggest distilling this information to program managers and decision makers who could better address some of the cloud and data needs to help better future model projections? That's a really good question. And I guess really the major takeaway for somebody who's trying to like make decisions with this would be to use a lot of care and be aware of the different conditions that you're modeling during. I think that it takes a lot more care and attention in selecting the combination of the boundary layer scheme and the cloud scheme, and also some of these other constants. It takes a lot of care and a lot of knowledge of like what's going on at the surface to accurately grab these sort of values. So I would say that people who are trying to read the models should keep that in mind and take what they're saying with a grain of salt sometimes in the polar regions over first year sea ice. But people who maybe want to advance the model, I would say to definitely start with looking at the clouds and the clouds during like the smaller particle size clouds, because I know that that's what is sort of unique about the Arctic, is that it's quite dry and a lot of our particles in the clouds are very small. And so that would be my starting place for addressing the cloud needs. As for the data need, just more observations really are vital to everything with this. Observations over different areas, over first year sea ice, longer experiments, just more observations to tune these models is really key.
So just for the audience, the general audience, there have only been 3 major wintertime experiments in the Arctic ever.
Wow.
Shiva in 98, 97, 98,
Yeah,
something
yeah,
like that.
97,
and
98,
ice,
yeah.
And then the recent Mosaic, that's it. So
Yeah.
in answer to your question about improving the models, there's a real lack of data to do it. So her work is actually incredibly important.
Yeah, the validation is huge, yeah.
Excellent tool.
Okay, thank you for coming.
Yeah.
Thanks for sharing.
Any other questions?
Yeah, you had a question.
Thank you so much for the great report and for the presentation.
Thank you.
I just want to ask if there are any publications on your research or.
Okay, so the question was if there's any publications, and so this research that I've just presented is largely unpublished so far. We have one publication that Vaughn is the first author on that looks at just the fluxes during ice, but not the cloud influence on the fluxes. And so we're working on a publication of the cloud, radiative forcing in the cloud influence first. And then we want to put something together as a modeling paper to put out to the modeling community. So that's sort of the plan for the publications.
And which cluster do you use for running the
So the question was which cluster I use for running WARF, and I use Cheyenne and Carr's supercomputer. I applied for time on Cheyenne and they gave it to me, and that was really great because that's also the computer that the people who develop WARF use. So if I had issues, it was really easy for them to like look at my code and help me out. They were really great.
It was a lot of work.
Yeah,
To
yeah.
get work done, get polar work done, that was a huge effort.
Mhm.
Have you used for that complement or that is cluster for this?
You can. The question was, can we use our WSU cluster for this Kamiak? You can, but there are a lot of permissions that and installations that like we maybe don't necessarily like have on the clusters. So it takes a lot of like communication with the people who are actually in charge of the cluster. I ran it on Aeolus a little bit. And I ran into some issues where I like needed to install some things that I didn't have the permission to install. And on Cheyenne, it's they have everything installed because they're the people who developed WARF, so it's all set up for that. But it is possible to run on Kamiak. It just is another hoop to jump through for sure.
And you did spend quite a bit of time trying to do that.
Yeah, on Aeolus, yeah.
This is such a
Yeah, I feel like it was something with the compiler too that was an issue.
I don't know, maybe now this me thinking out of the box, but could you think that the issue with the cloud parameterization scheme that is not like the result from the model doesn't capture the measurements well? Could be could be that issue related to the chemistry, because maybe if you tune in the aerosols influence on how clouds form, maybe that will help the results.
Yeah, that's a really good point. So what she said was, could the chemistry actually be part of the cloud issue? And I think definitely it could be. I haven't dug too much into the cloud code, so I don't know the answer to that for sure, but I think that that's a really like important thing to look into. And I think that, yeah, that's a great thought.
If there's nothing else, let's thank Sarah again. And if we'll just take a few minutes to let everybody clear out, and if you just leave your computer going.
I'm gonna stop the YouTube.